Hi everyone, welcome once again to another seminar of the IAG Astronomy Department. Thanks for joining us here or through our YouTube channel. And today's speaker is Dr. Raissa Estrela. Thanks, Raissa, for your presence here.
Thank you very much.
You're welcome. And Raissa got her PhD degree last year from Universidade Presbiteriana Mackenzie. And currently, she's a NASA postdoctoral fellow at the Jet Propulsion Laboratory. And Raissa works on the characterization of exoplanet atmospheres and the effects of stellar activity in the atmospheric evolution of exoplanets. And her talk today is entitled "Atmospheric Evolution and Habitability of Small Planets." So please turn off your microphones and your cameras during the talk. And if you have a question, you can raise your hand here in the Google Meet, or you can write it down in the YouTube if you are following through the YouTube channel. So Raissa, whenever you're ready, you can start sharing.
Okay, thank you.
Welcome.
Okay, could you confirm that you're seeing my screen?
Yes, we are.
Okay, all right. Well, thank you very much for the invitation to give this seminar today. Special thanks for the organizing committee, Maria and Reinaldo. It's a pleasure for me to give this seminar to IAG. I wish it was in person, but I hope that in the near future soon I'll be able to visit my colleagues and friends at IAG-USP. Well, today I'm going to talk about atmospheric evolution and habitability of small planets. As Maria already kindly introduced me, I'm Raissa Estrela. I'm a NASA postdoctoral fellow at the Jet Propulsion Laboratory in Pasadena, California. So in the last decades, we have seen a remarkable increase into the detection of exoplanets. And thanks largely to missions like the Kepler mission and the transit technique, we know today that the most exoplanets that have been discovered so far, they are small planets. And these planets, as you can see by this yellow circle in the figure, they have a size that ranges between the size of the Earth and the size of the Neptunes. And these planets, they orbit very close to the host star. We are now moving forward into the characterization of these planets, and we are trying to characterize the atmosphere of these worlds. And we want to understand about this atmosphere and answer questions about it, like, do they have secondary atmosphere? Are they backcores? Or how much envelope these planets have? So to understand the planets as we see them today, when we use space facilities like Hubble or ground-based telescopes, we also need to know about the past of this planet and understand about factors that can influence the evolution of the planet atmosphere. So there are many factors that can play a key role, like life, bombardment, migration, geophysical process, and the presence of a magnetic field. But in particular, there is one factor that can play a huge role, and that one is stellar activity, especially during the beginning of the planet's lifetime, because stellar activity can be more strong as the star is more active when it's younger. And this stellar activity can induce into the escape of the primordial envelope of the planet. A greater example of atmospheric evolution we can see here in our own solar system. So when we look into the terrestrial planets of our solar system, like Mars, Earth, and Venus, we know that these three planets, they started with a primordial envelope that was very different from what it is today. So this primordial envelope, it was mainly light gases like hydrogen and helium, and it was very thin. So this primordial gas envelope came from the planetary nebula. So it was accreted during the very beginning of the planet's lifetime. But as these planets are small, they lost this primordial envelope and they developed what we call secondary atmosphere. And the secondary atmosphere was still very different from what we see in the atmosphere of these planets today. When we look into Mars, we believe that this Mars had a secondary atmosphere that was thicker, warmer, and wetter, because we think that Mars had water in the past. But most of this atmosphere escaped to space due to the extreme ultraviolet radiation of the young sun and also due to the solar wind. So when we look into Mars today, we see Mars with this very thin atmosphere, almost nothing. And in the case of our planet, Earth, The secondary atmosphere was developed due to volcanism, mostly outgassing due to volcanism, and also there were some contributions from meteorites and comets. But the presence of life changed everything, and this atmosphere became an atmosphere that's oxygen-rich. While Venus, which is also considered to be an Earth twin in terms of size and density, it's believed that Venus was a way more hospitable environment in the past and had a thinner and cooler atmosphere, maybe even a water ocean, but all the water vapor molecules were broken apart by the ultraviolet radiation of the young sun. Remember that Venus is way closer to the sun than Earth. And hydrogen escaped to space. And subsequently, we had this rise in the level of greenhouse gases on Venus. So when we look into Venus today, we see a planet that is not very welcoming at all. It has this thick atmosphere, very rich in greenhouse gases, and that keeps the planet very warm. It's also important to highlight that neither Venus and Mars have a magnetic field. And this also could have played a major role into transforming these planets' environments, while our planet has a magnetic field. Now, when we look into exoplanets, small exoplanets, we also see signs of evolution into the atmospheres. So here in this plot, you see a distribution of planet size. You see that there is only small planets. And we see that there is a gap here in this planet size distribution that divides these planets into two categories. One is the planets that have larger radii because we believe that they still have a layer of hydrogen helium envelope. So these planets are called sub-Neptunes. And these other planets, the rocky planets, they are believed to be, they could be bare core sub-Neptunes. So sub-Neptunes that during the first million years of its lifetime, they lost their primordial hydrogen helium envelope due to the activity of the host star. So the host star is emitting extreme ultraviolet radiation that would induce into this atmospheric stripping in a very short time scale. And that would be the reason why we would see this gap here. So we see the transition between sub-Neptunes to rock planets, and some of these rock planets would be stripped core of sub-Neptunes. But it's also possible that these rock planets, they have a formation that's more similar to what we see in our solar system as well. So we have these questions to answer about terrestrial exoplanets. Are there remnant cores of sub-Neptunes due to atmospheric stripping, a process that we don't see in our solar system? Or are they shaped in a process that's more similar to Earth and Venus, how that collisions, for example, played a key role in shaping our planets? So to answer these questions, we need to look into factors that can shape the planet atmosphere and the planet core. And these factors are, you see here, insolation in the top panel. So the larger is the circle, the more insolation each of these individual planets receive. Forgot to tell you that this sample that you see here of smaller planets we took from the NASA Exoplanet Archive. So they are all observable, detected exoplanets. So again, so top panel is insolation, higher the circle, more insolation the planets receive, and the bottom planet, you see the density of each individual planet in terms of radii. And you see here what we highlight in this gray region here is the transition region, would be the transition region between being a sub-Neptune or being a terrestrial planet. So what we see here is that there are two trends. One trend is the low insolation planets that you see here in the bottom panel. They seem to form this continuous trend with the solar system objects that are present by the star symbol. And this could be indicated that these exoplanets with lower insolation level, they could possibly share a common formation mechanism with the solar system objects where collision plays a key role. While the high insolated planets, the blue ones that you see in the bottom plot, they form these continuous trends with the sub-Neptune's objects. And this could be an indication that these planets, they are likely to be bare rock planets of sub-Neptune, especially because they receive this high level of insolation. So to understand if these super Earth, the same super Earth that you see here that have received high insolation level, a really bare core of sub-Neptunes, as evolution suggests, we need to track the evolution of this envelope of the planets, of these planets. So we take the same super-Earths, high insulated one, and the sub-Neptune sample, and we're going to track the evolution of these planets in terms of mass and radius. So you see here the mass and radius diagram. To do that, we need to know how these planets were in the past, in the time that they were likely to lose in the first 100 million years, when they have the atmosphere that is going to be stripped by the UV levels. So we need to know the primordial population, and we need to know how was that environment, how was the UV flux that they received at that time. So to compute the primordial population of sub-Neptunes and super-Earths, we need to do 3 steps. One, we need to know what is the core mass of these planets. So for the sub-Neptunes, if you know the envelope mass that they have today, you just basically subtract this envelope mass from the current mass, and you get the core mass. For the super-Earths, we do a crude approach where we say that they are all bold core of sub-Neptunes. So they have no envelope, so their current mass is basically their core mass. So once we know the core mass of these planets, we can estimate the primordial gas that is accreted during the first million years of the planet lifetime, which is the envelope mass that's going to constitute the primordial envelope. So we use this relation that given the core mass, you can get the amount of primordial gas. And once you know the envelope mass, you can estimate the primordial radius envelope. So we know the primordial radius, we know the primordial mass, and then we need to know what was the UV flux at 100 million years. And to do that, we take the X-ray luminosity of the star as a function of age for each stellar spectral type, and we use a scaling relationship between the X-rays and the UV flux to get the UV flux that each individual planet received in that time. And with that, we can compute the photoevaporation, how much this planet lost in 100 million years during that very extreme environment. And here we're going back to the mass radius diagram. You see the change. So what you see here is the current population of super-Earths, the current population of sub-Neptunes, and the dashed line connects the current population with the primordial population, the one that we estimated. And you see the change after photoevaporation, which is mainly in radii. And the change in main radii is because this planet, they lost mass. So super-Earths, given our calculations, they are likely to have lost all their envelope due to photoevaporation, while sub-Neptunes, they lost in average 30% of their envelope. So just 1% of atmospheric loss is already sufficient to cause a significant impact in radii, because when the planet loses envelope, the planet shrinks. So these super-Earths that I showed here that have high insolation, that are likely to lose all their primordial envelope, they are ideal candidates to the search of a secondary atmosphere, especially secondary atmosphere if that are rich in light gases like hydrogen. And a great example of such planet that have high insolation is likely to have been a sub-Neptune that lost all the primordial atmosphere and became a bare rock super-Earth is the J1132b. So the J1132b is a planet that have a mass and radius quite similar to that of our own planet. Also, the density is quite similar to our planet, but it's orbiting very close to the host star and have insolation that is 19 times the insolation that our planet receives from the sun. And it's also a very warm planet with 529 kelvins. So this planet was observed with the Hubble telescope. So it has this public available data, and we can use the data to estimate if this planet still have an atmosphere or not. So we can confirm what we predict, that this planet would have lost completely its primordial envelope. So we're going to use a technique that's called transmission spectroscopy. This technique is it's the most used technique today to detect atmosphere in exoplanets, and it's an indirect method. We are not seeing the atmosphere of the planet itself. What we see is the light of the star that passes through the atmosphere of the planet, and if there is an atom or molecule present in that atmosphere, these molecules or atoms that can absorb the stellar light at a certain wavelength. And we're going to see this absorption signal with our telescope, can be Hubble or a ground-based telescope as well. So we can see the sign of absorption in the satellite during the transit of the planet. So during the transit of the planet is passing in front of the star and is going to block part of the starlight. So it's going to dim the brightness of the star, and we can see this in the transit light curve. So this dim, there is this dim, we see this huge transit depth here, because the transit is blocking, the planet is blocking the starlight portion. And if there is an atmosphere, this atmosphere is going to appear as an opaque disk at a certain wavelength, because as I told you, molecules and atoms, they are going to absorb in a certain specific wavelength. So this will cause the atmospheric disk to show as an opaque, and it's going to change the planet depth. So we see this change in the transit depth as a function of wavelength. So this creates what we call transmission spectra, and you can see here the transit depth variation as a function of wavelength. So with this transmission spectra, we can access different information of the exoplanet atmosphere. In the visible, we can see signs of haze, which can induce Rayleigh scattering. We can also see signs of atomic absorption, and we can also see signs of molecular absorption like water, methane in the infrared. So there are two instruments on Hubble that can detect these signatures. With these, we can see mostly the visible, so mostly atomic or Rayleigh scattering, while WFC3, another instrument on Hubble, cover the near-infrared portion, and it can detect the molecular absorption. So going back to the 1132, now you see here the transmission spectra of this planet. So the transmission spectra of this planet was obtained, as I told you, with Hubble, the instrument WFC3. And then what we see is that the atmosphere is composed, our model, our atmospheric retrieval model, to interpret this transmission spectra indicates that this planet is composed of mainly hydrogen, with a combination of hydrogen cyanide, you can see here, some methane, and also aerosol, which is given by this aerosol scattering. So this atmosphere is composed basically by very light molecules. So it's a very light, puffy atmosphere, so it's easy to detect. But you must be wondering, how can a planet that have the same mass as our planet can retain atmosphere that's basically hydrogen and helium? And that's true. The planet, if you look into the escape velocity of this planet compared to our planet, we see that the planet does not have sufficient gravity to retain hydrogen and helium. So it has a rate, hydrogen and helium rate, that's very similar to our own planet. So you can see that hydrogen and helium, they can escape, they can reach enough velocity to escape the atmosphere of this planet, which is indicated by the pink symbol here. So the planet would need some hydrogen replenish mechanism to counter the thermal escape of hydrogen. And what we propose as a mechanism to replenish the atmosphere with hydrogen is outgassing through volcanism. So this planet is tidally located with the host star, which means that this planet has a tidal heating that keeps the internal parts of the planet hot enough to remain liquid. And this planet would have a magma ocean, this hot magma ocean, where dissolved in this magma ocean, there is hydrogen that was accreted during the planetary accretion phase. The same hydrogen that formed the primordial envelope of the planet would have been dissolved in the magma ocean of the planet. And now this hydrogen that was trapped there would be released back to the atmosphere through outgassing mechanism. So our collaborator, Paul Riemer from Oxford, he did some outgassing models to see if they would explain our transmission spectral data. So he did two models. One is based on nitrogen-dominated magma, and another one is a hydrogen-dominated magma. So the nitrogen, which is represented by this green cube that you can see here, it provides a relatively poor fit to our data, while the hydrogen-dominated magma provides a very good fit to our data. So this hydrogen magma outgassing model seems to explain what we see with Hubble. So this atmosphere, this outgassing that we would see in the J1132 is a very different outgassing that we see in our own planet. So what we see there would be outgassings of very reduced gases like hydrogen, methane, hydrogen cyanide, while in our planet we see more water vapor, CO2, and sulfur. But it's also possible there is some suggestions that Earth, in the primitive Earth, could also had release reduced gases like we see in the J1132. So the J1132, if we look into these nice pictures of the configuration of the surface and atmosphere and compare with our planet Earth, we see how different this planet is from our planet. Although they have the similar mass and size, these planets are so different. So the J1132, as we see, it's a planet that's very warm. It has 256 Celsius, and we believe that it has this magma ocean with hydrogen trapped and a lot of volcanic activity going on that's releasing hydrogen back to the atmosphere. And the atmosphere is very hazy, which we detect with Hubble. While our planet is way more cooler, it has 15 Celsius, and it has very lower volcanic activity nowadays, and it has an atmosphere that's basically nitrogen dominated and contains oxygen, while the J1132, the atmosphere is rich in hydrogen. So going back to the transmission spectra of the J1132, we see that the atmospheric signs here that makes us be able to detect the atmosphere in this planet is aerosol scattering. So aerosol scattering is also known as Haze. And Haze is very common in our solar system as well. We see Haze in the gaseous planets like Jupiter. We see Haze also in the dwarf planet Pluto. There is this beautiful image taken with the New Horizons missions that show this smooth layer of haze in Pluto. And even in Titan is very hazy. It has also this organic chain of haze. So why not take advantage of Hubble to explore haze in other planets, as we can see as a great example that in the J1132b planet, haze was the main feature to detect a secondary atmosphere. So Hubble has an instrument called STIS that can help us to see signs of haze in these other worlds. So STIS has two filters. One is the G430L that covers from 0.3 to 0.5 microns, and the other one is kind of a complementary filter that covers from 0.52 to 1 micron, close to the near infrared. So you can see here the throughput, which is the efficiency at each wavelength for these two filters. So the data reduction steps for STIS is the following. Once we have the 2D image of the spectra in each filter, you can sum the columns of the image to obtain the 1D spectra. So you need to remove any cosmic ray as well. So you see here for this target HAP11b, the 1D spectra for G430L and the 1D spectra for G750L. So in the case of the G750L, there are some fringes that is induced by systematics, in the instrument systematics, and we need to correct these fringes with a flat fringe correction. So you can see the before and after. And we also need to calibrate the spectra as well. And we do that in two different ways for each filter. For the G750L, we use a more simple approach. We basically can model the spectra with a black body function times the efficiency of the filter, the throughput. While for G430L, we need to take a model that's closer to the spectra that can represent well the spectral features. There is a strong spectral feature here. I think it's magnesium, if I'm not wrong, that we need a Phoenix model, which is a library of stellar spectra that can give you the closest stellar spectra to your target in terms of metallicity, effective temperature in log G. So here you can see for G430L, the Phoenix model times the throughput of this instrument that we use as a model to calibrate the spectra that's in blue. So we can basically scale and shift this model to calibrate the edges of our observed spectra. And here you can see the calibrated spectra for each frame for HATP11b. So once you have the calibrated spectra, you can basically sum in the wavelength axis to obtain the broadband light curve. And here in this, each color here represents a different filter from Hubble. So you see G750, G430, and there is even some filters from the other instrument, WFC3. And we can model this white light curve to extract information about the planet. So we model that, and we do MCMC retrieval that can give us information about the orbital solution of the planet, like the time of the mid-transit, inclination, same major axis. And we can also use an instrumental model because there are some systematic trends that is induced by the instrument that we also need to take into account. And there is also stellar limb darkening. We also need to take into account the stellar limb darkening, which is an effect in the edges of the stellar disk, which is less brighter than the center. And it's also going to impact the transit. So we also need to model that. And the transit depth. For the spectral light curves, instead of summing in all wavelength axis, we are going to sum just the spectral point associated to each wavelength beam. So with that, you can obtain these spectral light curves that you see here on the right. So you see the spectral light curve associated to each of these wavelength beams from STIS. And we can model these spectral light curves in a very similar manner to what we did with the white light curve, except that now we are going to retrieve only the wavelength-dependent parameters, which is the instrument model, stellar limb darkening, and the transit depth. So once you obtain this transit depth for each spectral light curve, you can build the transmission spectra. And we put all these data reduction and calibration process in our JPL pipeline, Excalibur, which aims to provide a uniform analysis of Hubble and Spitzer observations for all public available data with transit observations. So currently we have about 90 planets, and this is going to provide a major step towards comparative planetology of exoplanets, because now we are performing everything from all the data reduction steps in a similar manner instead of comparing results from different pipelines as we do nowadays. Most of the works nowadays in the exoplanet community is still being doing by using different pipelines, and that is very difficult to compare. So our pipeline aims to produce transmission and also emission spectra at full resolution in the case of WC3, or high instrumental resolution in the case of STIS. And also we need to have an atmospheric retrieval package to interpret these transmission spectra. And this retrieval package is called Cerberus and is aimed to provide the best set of atmospheric parameters. We aim to make this data public available very soon. So we're going to have a platform that you can see here where anyone would be able to access the broadband, the spectral light curves, and also the transmission spectra of the exoplanet. So currently on Excalibur, we have STIS, which I'm presenting this work, and the goal of STIS is to probe atmospheric haze. We also have WFC3. WFC3 probes molecular absorption like water and methane. And we also have Spitzer, which provides 2 channels that can give a robust estimate on the planet X2O ratio. So in the case of STIS, Cerberus, the atmospheric retrieval is mainly focused in interpreting the haze in the exoplanet. So to do that, we need to start with a Jupiter haze dense profile, and we parameterize the Jupiter haze profile in terms of a multiplicative scale factor of the optical depth. We also parameterize the maximum density, the peak of the haze cloud. So this peak of the haze cloud can go up or lower in terms of the pressure. So here you see the atmospheric profile. So the haze peak can go up and down. And also the thickness of this haze cloud can also vary. So a great example you can see here is for this planet WASP-69b. We recently published these results into the AJ. And what you see here is the G430, G750, and the WFC3 filter as well. So when we combine all this data, we can get great information on the planet's atmosphere. With this, we see this railing scattering due to aerosol haze that cover up to 10 scale height. So this haze, Cerberus atmospheric retrieval, indicates that this haze is widely distributed in the atmosphere of the planet and go up to very low pressures, up to microbars. So this haze is in the upper atmospheric layer. And this haze could be preventing us from seeing this water filter here. So you see that this water filter is very suppressed, and that could be due to the presence of haze. So this widely distributed haze was predicted before by theories, and now we confirm it with our observations. So we aim to do more kind of this work for most of these planets that are already in our pipeline, and maybe results will come soon. So haze is also very important for habitability because they play a key role into regulating the temperature and the radiation flux of the planet. They can also provide organic material that can help in building the blocks of life, and we see organic haze in Titan, for example. And also haze can provide a shield from ultraviolet radiation. And this third point is particularly important because we know that stars can be very active. And there are many flares that were detected in other stars with Kepler and K2 observations. And these flares, they can release a significant amount of ultraviolet radiation. So here you see two examples of superflares. One is in a solar type star, Kepler 96, where this Kepler data show a superflare that happens in the mid of the transit of the planet that's orbiting this star. And in the bottom, you see a complex superflare that was detected with K2 for TRAPPIST-1. And TRAPPIST-1 is a very interesting system for habitability because it has 7 Earth-sized planets, and 3 of them are in what we call habitable zones. So they are in a region where these planets could have liquid water. So these superflares could have a significant impact in the habitability of planets in the habitable zone of these 2 stars, because as I told you, they can increase the UV radiation. And also they can cause potential effects in the atmosphere of the planet, like atmospheric loss. As we saw in the very beginning of the talk, that UV from the host star can induce an atmospheric stripping. And it can also affect the composition of the upper atmosphere. They can even destroy ozone. And ozone is very important. We know that ozone layer is very important here in our planet. And it's protecting us right now from very harmful UV radiation like UVB and UVC. So we did this work where we took these flares observed in the visible for TRAPPIST-1 and Kepler 96, and we tried to estimate the UV radiation using as a template the sun for the solar analog Kepler 96 and ADLEO for the M-DOF TRAPPIST-1. So we took flares that were observed in these 2 stars in the UV, and we scaled that for the flares that were observed for this Kepler 96 and TRAPPIST-1. So once we get the UV radiation that comes from the flare, we can see how much of this UV radiation would be attenuated by atmosphere in the habitable zone of these planets. So we use a primitive Earth atmosphere that has no ozone and atmosphere with ozone. And then we compute the UV flux that arrive in the surface, and we estimate how much that would impact life as we know here on Earth. So we took an extremophile, the nococcor radiodurans, that can survive extreme radiation, and a regular microorganism, Escherichia coli, that lives in our gut. So I'm going to pass very quickly through these results because of the time, but here is just to show you quickly the surface flux that arrives due to the TRAPPIST-1 superflare at each instant of the flare. So this would be the surface flux that arrives pass through these 2 types of atmospheres that I told you about. And we see that for oxygenic atmosphere, most of the harmful UVC and UVB would be prevented to reach the surface of the planet. So we took these UV levels that we computed for these 3 habitable zone TRAPPIST-1 planets and also for the Kepler 96 system. And we tried to see how much of this UV that arrives in the surface of the planet how much that would be enough for these two microorganisms to survive. So we know the dosage that this microorganism can survive because of laboratory experiments estimated that. So you can see here, Deinococcus rhabdoideus can survive to more extreme UV. And compared to the UV flux that arrive in each surface of the planet, we see that in the case of Kepler-96, this microorganism would need ozone, a present-day atmosphere with ozone in order to survive. While in the TRAPPIST one, the UV levels is not that much, is not that higher. It's less than in the solar analog. So these bacteria would be able to survive also in atmosphere with ozone, but Deinococcus rhabdoideus could even survive in atmosphere with no ozone. So the flux arriving the surface of the planet is enough to even keep Deinococcus rhabdoideus in the TRAPPIST-1 habitable zone. So given all these information that I gave to you today, I'm going to leave some directions for future research. So we saw that highly radiated super-Earths, they are very likely to have lost their primordial atmosphere due to photoevaporation or any other atmospheric stripping process. So these atmospheres, they are these planets that likely lost their primordial content, they are desirable targets for secondary atmospheres. And we see that in the case of the J1132, the secondary atmosphere is originated through outgassing. So we need more investigation of how likely it is for this kind of planets that are highly radiated, how likely it is for them to develop a secondary atmosphere. So we need more observation, probably with the James Webb Telescope near soon. We're going to be able to understand how likely it is for these to happen, not only in the J1132b. And we need to take more advantage of Hubble to understand about haze in exoplanets, as haze can be used to probe secondary atmosphere in small planets, which was the case of the J1132b. And third, we need a better understanding of the concept of habitability. We see that stellar activity is one of the main factors for habitability because the stars can have these flares that they are way more powerful than our own solar flares, and they can induce atmospheric stripping, and they can also affect directly the presence of the life in the surface of the planets. Thank you very much.
Thank you, Raissa, for this very interesting talk. So I have a couple of questions myself before I let others to ask. So first, I'm sorry because I'm not really into this subject. Can you please comment very briefly what you actually mean by insolation?
Yeah, so the insolation is basically the flux that comes from the host star that reaches the planet. Like our star, the sun, is emitting some luminosity right now, and you can calculate how much of that arrives in the surface of the planet. So it's basically, that is the insolation. It's basically the flux that's received by each planet.
Okay, so it's just the flux.
Yes, exactly.
Okay. And related to that, when you were commenting about the evolution of the envelopes, you have the, if I am not mistaken, you have the rate of fluxes, UV flux over X-ray flux.
Let me go here.
Yeah.
So let's go back. Yes, it was this one, or you're talking about this insolation here?
No, the previous one. Yeah, here. Mm-hmm. This FX is the X-rays. Where these X-rays are coming from?
So we took these X-rays. It was basically in the literature. There are some. So these works that you see here, they used stellar clusters to determine the X-ray luminosity through age. So we took these relationships from these previous literature works in order to estimate the X-ray luminosity for our targets. So because these targets, when we see them today, they have like giga years. They are around the same age that we are. or a bit lower, like a gigayear, but we want to estimate how these X-rays, how the UV flux were in the past. So we need to use these X-rays stellar age relationships to get the UV flux around a million year, which when the atmospheric stripping is more likely to happen because the star is expected to be more active, to have more UV flux, higher UV flux. So we took these relationships between X-ray and luminosity and stellar age from the literature, and we estimate the UV flux at 100 million years using this scaling relationship between X-rays and UV flux for each target of the sample, super-Earths and sub-Neptunes. And with that, you can compute the photoevaporation due to UV for each target and estimate how much mass they lose in their envelope, the primordial envelope.
Mm-hmm. Okay. Mm-hmm. Thank you. Now it's more clear. So let's go to the hands. I think Reinaldo was in the list for asking a question.
Thanks, Raissa, for the talk. I have two questions.
Sure.
Maybe you answered during your talk and I did not get. You showed two microorganisms that are used to define the survival zone. I think in slide 42 or something like this.
Let me go.
Why is that choice? Are those the most resistant organisms to UV radiation on Earth?
Mm-hmm. Yes, exactly. Is that your question?
Yes, yes. And I have another question. Yes, it was my doubt to why these two. And my other doubt is that we learn from, I remember at least that a part of our atmosphere was built by activity of the life itself, that it builds some shield for UV. So before this this activity of the life itself, was the Earth with respect to the UV flux in the habitability zone?
Okay. If the UV flux would have any part in the primitive Earth?
Yes, if the Earth could be considered in the habitability zone, considering the UV flux. Because I don't know if this concept is correct, so that I learned somehow that the life itself built some shield against UV flux or
okay. Let me start for the first one. So the Deinococcus radiodurans is one of the most well-known now bacteria nowadays because for being what we call extremophile, that can live in very hazardous environments. And if you look here, this is the flux that the dosage for 10% survival of each of these bacteria. So you can see that Deinococcus radiodurans can survive way more UV flux than the Escherichia coli. So here you have 553 joules per meter square, while Escherichia coli survive only 22 joules per meter square. So this bacteria here, we took this one because it's way stronger. It can survive more UV hazardous environments, while Escherichia coli is more like a normal bacteria that lives in our gut. So it doesn't. It's like a normal bacteria. It can't survive to this extreme environment. So we could compare both and see how they would deal in these worlds that have superflares. For the second question that you asked about the UV environment in the young sun, I know that in the young sun, we had what we call it's the paradox young sun, because believe it that the sun had a low UV flux environment for a certain time period. And our planet, as I told you, it has this ozone layer nowadays because the ozone layer was built by the presence of life. So ozone layer is made of oxygen, right? So this ozone layer protects us from the UV, for the harmful UV nowadays. But in the past, before life was not there, we don't know. Probably the primitive Earth was a way more less hospitable environment because there was no ozone layer. So all this UV was reaching the surface of our planet. So not very, maybe not very welcome for life. But also it's believed that the sun was it was fainter than it is today for a period, and that could have helped life to develop as well. I don't know exactly how much is the UV level of the primitive sun. I can give you the information right now, but I know that there is this young faint paradox in the young sun that led to the lower or fainter sun, and that might have helped life actually to develop in our planet. But I think there is still more studies needed in that field in order to understand how was our primitive environment in that time.
Thank you.
Okay, so let's move on to Roderick. Please, you can ask your question.
Thank you, Raissa, for this wonderful overview of your work. We're certainly paying attention to this for the development of the GMT, right? Where this will be a major area, but that's still very far away in the future, about 10 years. So I wanted to ask you, since what you've presented here is all based on with C3 and STIS with Hubble, whether you think it's possible to detect the atmosphere in H and K band, maybe more in K band from the ground using 8-meter telescope. Given that you showed in your introduction, right, that's especially in K band, the effect should be larger.
Yeah, I don't have much experience with the ground-based facility, but actually we're trying to do that. Right now we have an instrument on Paloma Observatory, which is called NESI. And NESI is a spectrograph that observes the K-band, but we are still trying to make some, mostly we are trying to observe giant planets right now because they have the larger transit depth, so it's easier to detect, right, compared to these small planets that were observed with Hubble. And also we have the atmospheric effects from the ground, which doesn't help much. And we need to better understand how to remove the telluric effects in order to get a precise transmission spectra. So Paloma, I believe it has 6 meters, the telescope, if I'm not wrong. And you asked it with 8. Sorry?
5, I think.
5, okay, yeah. Hubble has 6, so I might be mixing both. And but yeah, so far we are trying with giant gaseous planets. I think for small planets, that will be that's our goal in the future, using Paloma and NESI. But first of all, we are trying with the giant planets yet because they are puffy, they have more atmosphere, they have this huge envelope of hydrogen and helium. So the atmospheric scale height is larger, so it's easier to detect any signal. But I believe with future larger 8 meters, that would be more favorable towards small planets, but I would say more like sub-Neptunes. I'm not sure yet about very small planets like the J1132. The J1132, yeah, if you find good host star with bright stars, so I think TESS is going to help us in that aspect because TESS is looking to bright stars. So that could give us a target of a small planet with a bright stars or M-Dolphs as well, like planets like TRAPPIST-1 orbiting M-Dolphs. Maybe we can use TRAPPIST-1 style of planets with 8 meters telescope, but I think that's still complicated. We did the TRAPPIST-1 with a VLT in the past, but it was still harsh to get a precise transmission spectrum. The other was still very hard. So we will see. But I think with the ground-based facility, we might need to wait for the extreme large telescopes like ELT. But yes, as I said, I'm not very experienced into the ground-based facility. I work more in the space-based. But yeah, I hope that in the near future, with the extreme telescopes, we're going to be able to move towards small planets in the ground-based as well.
Thank you. Maria Victoria, may I ask a second question?
Yes, sure. Please go ahead.
Is there a connection between the aerosol scattering, the amount of aerosol scattering, and your hypothesis that the hydrogen is being replenished by large volcanic activity?
Yeah, so there are some scattering that see that could be due to photochemistry of methane, and this methane it's coming from outgassing, basically from volcanism. So yes, the aerosol scattering that we would see in that would be created by the gases that constitute the atmosphere now, like methane, photochemistry of methane.
Okay, thank you.
Mm-hmm.
Okay, so any further question? Okay, if there is no more question, we will thank you again, Raissa. Many thanks for this wonderful talk. And well, I thank everyone who is joining us, especially through YouTube and here. And well, vamos cortar.
Thank you. Obrigada, muito obrigada.
Obrigado, Raissa.
Richard.
Quem quiser comentar algo, abrir câmera, microfone, também se sinta à vontade.